Okay, so now let's introduce some concise and rigorous syntax for representing the temporal patterns that we discussed before. We start by fixing a set atoms of atomic propositions, or atoms for short. Often we will write P, Q, R, etc. for atoms, but sometimes we will use more meaningful names as well. The LTL formulas, usually denoted phi, psi, etc., are defined by the shown grammar. The symbols that are used to put formulas together for building larger formulas are called connectives. The connectives are not, or, and, implies, next, eventually, always, until. This is the usual BNF style definition, meaning that formulas are defined recursively as follows. Any atom is a formula. If phi is a formula, then not phi is a formula. If phi is a formula and psi is a formula, then phi or psi is a formula, and so on. In particular, if phi is a formula and psi is a formula, then phi until psi is again a formula. As usual, we use parentheses when needed in order to make the formulas unambiguous. This is an example of a correct formula, which is read always P until Q until R. Sometimes we don't need parentheses, as in this formula, which is read always eventually P, which expresses one of the patterns we discussed before. We distinguish two kinds of connectives. The propositional connectives, not, also known as negation, or also known as disjunction, and also known as conjunction, and implies for implication. And the temporal connectives. Next, denoted by circle, eventually, denoted by diamond, always, denoted by box, and until, denoted by capital U. So this is how we read the temporal connectives when applied to any formula phi. Circle phi is read next phi, diamond phi is read eventually phi, box phi is read always phi, and phi u psi is read phi until psi. Another way to classify connectives is into the unary ones, not, next, eventually, and always, and the binary ones, which are and, or, implies, and until. As a matter of parsing, we assume that the unary connectives have higher precedence than the binary connectives. For example, when we write always phi or psi without parentheses, what we mean is this: parentheses, always phi or psi. Okay? This is because always, which is unary, has higher precedence than or, which is binary. This convention allows us to write formulas without using too many parentheses. You should be familiar with such parsing aspects from the study of programming languages. With logics, it's the same thing. Here are more examples of correctly constructed formulas. By the way, this does not mean that they are true. We have not yet clarified what truth means for LTL. It just means that they are syntactically correct. They are syntactically correct because they are built starting from atoms and applying the unary or binary connectives to correct numbers of arguments. 1 for unary connectives and 2 for binary connectives. Let's read these formulas. Eventually P and always Q implies P until R. Eventually P implies always R, or non-Q until P. P until Q until R. Always eventually P implies eventually Q or S. By contrast, the following are not correct formulas. In the first example, the binary connective U is applied to one argument, which is wrong. And in the second example, the unary connective always is applied to two arguments, which is again wrong. So until should be applied to two arguments and always should be applied to one argument. Okay, time for an exercise, which is a way for me to check that you are still awake. First, please give 5 more examples of correctly constructed formulas. Among these, one of them should be a single formula that contains 5 atoms. And another one should be a single formula that contains 3 occurrences of eventually, 1 occurrence of always, and 2 occurrences of until. After you constructed them, please read them aloud. Moreover, give 2 examples of incorrect formulas that do not contain until or always.